Welcome back, guys. In this video, we are doing the same thing that we did in the last video. This time, we've got a function that has some vertical asymptotes. We're determining the intervals where the function's increasing and decreasing. We're determining the intervals where the function is concave upward and concave downward. And we're classifying relative extrema. We're finding them and classifying them. We'll do that using the first derivative test, and then we'll confirm using the second derivative test. Then we'll find points of inflection of the function, and then we'll sketch it using all of the information that we found. The way we always start, it's a very good way to always start, is we'll find the domain of the function. You just need to figure out where is this function well defined. And this time, there are actually some x values that we have to leave out. This is the set of all x such that the following is true. We need to include or exclude all the x values that cause 3 problems. We don't want to divide by 0, we don't want to take even roots of negative numbers, and we don't want to take the logarithm of a negative number or 0. There are no even roots, there are no logarithms, so the only danger is dividing by 0. We would be in trouble if this denominator x squared minus 4 were 0. So the domain is a set of all x such that x squared minus 4, that denominator, is not equal to 0. So you set the denominator not equal to 0 and solve for x. So that means x squared is not equal to 4. And if you take the square root of both sides, don't forget the plus or minus, you get x is not equal to plus or minus 2. So here's our domain. It's everything except negative 2 and 2. Okay. So that's it. Now normally we don't use set builder notation in calculus class. Normally we use interval notation. So I've got this interval, and this interval. We read the intervals from left to right. So the domain is negative infinity to negative 2, union negative 2 to 2, union 2 to infinity. So it's those 3 intervals. Now what does that mean for us? Well, that means this function is undefined at those 2 x values. Since the denominator is 0 at x equals plus or minus 2, and the numerator isn't, what we have are vertical asymptotes there. Now, if x plus 2 or x minus 2 is a factor of the numerator, our graph might have a hole in it, that removable discontinuity that we talked about in the chapter on limits. But that's not the case here. Even if I factor this as much as possible, that denominator factors to x plus 2, x minus 2, the numerator doesn't factor. So these factors, well, we can't just reduce them and then take a limit from there. So we don't have any removable discontinuities here. These x values correspond to asymptotes. So keep that in mind. Those x values are going to have to show up on our number lines when we're determining the intervals where the function is increasing and decreasing in concave up and concave down. But those x values cannot correspond to points of inflection because there are no points on the graph there. It's an asymptote. And those x values cannot correspond to relative extrema. Can't have a max or a min where the function's undefined. But they do need to be on our number line. So keep that in mind. Our domain is this. X equals negative 2 and x equals 2 need to be on the number line when we determine the intervals where the function's increasing, decreasing, concave upward, and concave downward. So now let's determine the intervals where the function is increasing or decreasing. The way we do that is we find the critical points. If you're taking Calculus 1, you're in this chapter, when in doubt, just take the derivative. It's probably a good way to start. When you're finding critical points, you compute the derivative, set it equal to 0, and solve for x. Okay, I'm going to use this version because it's easier to compute the derivative of that. So g prime is the derivative of this quotient, x squared plus 4 over x squared minus 4. I have to use the quotient rule. So we get low, bottom function. D high, the derivative of the top function, is 2x, minus high, it's x squared plus 4. Don't forget your parentheses. D low, which happens to be 2x, all over low, the bottom function squared. It's x squared minus 4 quantity squared. Okay, now we'll distribute the 2x here, and we'll distribute the 2x there. So we get 2x times x squared is 2x cubed. 2x times the negative 4 is negative 8x. If I distribute the 2x here, that's a good thing. I get 2x times x squared is x cubed, but I'm subtracting it, so it's negative 2x cubed. And then 2x times the 4 is 8x, but I need to distribute the negative to that as well, so it's going to be a negative 8x all over this. And the 2x cubes reduce, and we end up with a negative 16x over x squared minus 4 quantity squared. I keep calling it f. I'm in the habit of calling all my functions f for function, but that's not the case. This function's name is g. It's sort of rude to call it by the wrong name. So yeah, I want to take the derivative of g, I got g prime, and now I need to set g's derivative equal to 0 and solve for x. Well, the only way a fraction is 0 is if the numerator is 0. So that tells us that negative 16x must be 0. And if I'm trying to get x by itself, clearly x has to be 0. So that's one critical point. Now, other critical points can come from x values in the domain for which the derivative is undefined. So you have to ask yourself, are there any x in the domain of g for which g prime is undefined? Keep writing f. G prime is undefined. Are there? Say, well, it's undefined when the denominator is 0. That's at x equals plus or minus 2. But those aren't in the domain. So this is our singular critical point. It's our only critical point. Okay, so now we're going to do a sign analysis of the first derivative. It sounds better to say conduct. We're going to conduct a sign analysis of the first derivative. Now, when you do your sign analysis, you need to put the critical points on the number line and any x values for which the function is undefined, because those two vertical asymptotes that correspond to x equals negative 2 and positive 2, those define intervals. So I need to put those on here too, but I need to remember that those don't correspond to relative extrema. So I'm just going to draw a big line like this to remind myself that x equals negative 2 and x equals positive 2 are vertical asymptotes. So let's say we should graph, in general you want to graph the critical points and let's say any vertical asymptotes on the number line. And then we'll do our sign analysis of g prime. Now g prime is a quotient. It's negative 16x over that product, or over that expression squared. So I'm just going to split it into the factor in the numerator and the factor in the denominator. Now that factor in the denominator is 0 at negative 2 and 2, but the rest of the time I'm just taking a number and squaring it. So it does not matter what x is. As long as it's not negative 2 or 2, we're going to get a positive number out of that. Now negative 16x, well, that only changes signs at 0. when we're on this interval, we have a negative value for x. Substitute in -3. -16 times -3, that's definitely positive. Or on this interval, substitute in any x value on the interval. I pick -1. -16 times -1 is positive. So g prime is a positive divided by a positive on that interval, so it's positive. And over here, g prime is a positive over a positive, so it's positive. So the function is increasing on this interval and increasing on that interval. Let's see what happens over here. Substitute in x equals 1, you get -16, that's negative. Substitute x equals 3 here, you get -48, negative. A negative divided by a positive is negative, and a negative divided by a positive is negative. So that means g prime is negative. If g prime is negative, the function is decreasing. Okay, so they asked us to find the intervals where the function is increasing or decreasing. Our sign analysis got us those intervals, so we just have to read our sign chart now. The function is increasing. The original function is increasing. Not g, but it's the original function, is increasing on -infinity to -2 and -2 to 0. A lot of students want to just say -infinity to 0, but you do have to skip this x value because that x value is not in the domain of the function. The function's decreasing on 2 intervals as well, from 0 to 2 and 2 to infinity. Okay, and now we can also use the first derivative test to determine whether x equals 0 corresponds to a max or a min. I think we can see it just from the arrows. The function goes from increasing to having a 0 slope to decreasing. We're going to have a relative max at 0. So I'll say our next step is to use the sign chart. And the first derivative test. To find any relative extrema. And it looks like we only have one. We've got a relative max at x equals 0. So g of 0, that was 0 squared plus 4 over 0 squared minus 4. You're replacing the x with 0. And this is what you get. 4 divided by -4 is -1. And according to this, that's a relative max. The function has a relative max of -1 and it occurs at 0. Okay. What else were we asked to do? We want to determine the intervals where the graph is concave upward and concave downward. We want to confirm our result for x equals 0 using the second derivative test. We want to find any points of inflection, and then we'll sketch the graph using all of this information. So to determine the intervals where the graph is concave upward or concave downward, we're pretty much going to do the same thing that we just did for the first derivative to the second derivative. We don't call it finding critical points, but we're going to find the second derivative and set it equal to 0, just like we did when we were finding critical points. Oops. And some work from another class. Okay. Trying to go through all of my scratch paper. I don't like to waste paper, but I go through a lot of it. Okay. So we're trying to determine the intervals where the graph is concave upward and concave downward. The first thing you do to do that is you compute the second derivative and set the second derivative equal to 0 and solve for x. So our first derivative was -16x over the quantity x squared minus 4 quantity squared. And we're taking the derivative of the first derivative to get the second derivative. So we'll use the quotient rule. Remember that mnemonic, it's low d high, so it's the bottom function, times the derivative of the top function. The derivative of a constant times x is just a constant, so that's low d high, minus high. High is negative 16x, top function, times d low. Now the derivative of the bottom function requires the chain rule. I've got a function squared. The derivative of a function squared is 2 times that function to the 1 less power, inside function is x squared minus 4, times the derivative of the inside by the chain rule. You do not have to write this step. I'm just writing it for those people who are still a little iffy on the chain rule. So we'll write that down. So that's low d high minus high. This is all d low, all over low low. If I'm taking something squared and I'm squaring it, we multiply those exponents. The 2 times 2 gives us a 4. So that's our second derivative. It's pretty ugly right now. We need to factor it so that we can set it equal to 0 and solve for x. So I'm going to clean it up a bit. I'll factor out that negative 16. Oops, and I guess I need to compute that. That's 2x. And now I've got a 2 times 2x is 4x, and 4x times 16x is 64x squared. I've taken care of that, I've taken care of that and that. The only thing that's left is that x squared minus 4. And this is all divided by x squared minus 4 to the 4th. Okay. Now, when I'm factoring from here, I look at this term and I look at this term. I'm thinking of them as terms. I'm thinking of this is 1 unit and this is 1 unit. And I'm saying to myself, well, what do these guys, what do they both have in common? They both have a negative 16 in common, or a 16. I'll factor out the negative 16. And they also have an x squared minus 4. This one has 2 of them, but that one has 1. So we can take out x squared minus 4 from both of them. And then I ask myself, negative 16 times x squared minus 4 times what will give me the first term? Well, I've already got the negative 16 and the x squared minus 4. I need one more of those. So that goes right there. And then I ask myself the same thing. This times what will give me this? To get a positive, I'll need a negative. Negative 16 times negative 4 would give me the positive 64. I need an x squared. And the x squared minus 4 has already been factored out, so we're good. So there's not really much going on over there. Now I can simplify that expression in brackets. Brackets are overkill a bit. We've got x squared minus 4x squared is negative 3x squared. Okay, so that's our second derivative. We're going to set that equal to 0 and solve for x. The only way a quotient, oh, whoops. I've got an x squared minus 4 in the numerator and denominator. I can reduce that. There we go. Now we're good. So now I'm setting this equal to 0 and solving for x. The only way a fraction is 0 is if the numerator is 0. So I've got negative 16 times negative 3x squared minus 4 equals 0. And you could factor out the negative and divide both sides by 16. Oops. And right away, I hope you see that there are no real solutions to this. If you're not sure, just go ahead and try to solve. See what happens? You get x squared equals that negative number. That's possible, but not in the real number system. We'd have x equals plus or minus the square root of a negative, and that's not what we want. So g prime is never 0 in the real number system. Okay. are there any x, we also have to think about x values in the domain for which this is undefined. Well, this is undefined when the denominator is 0, but the denominator is 0 at x equals plus or minus 2, and those are not in the domain. So g prime is never 0, and g prime, or g double prime, excuse me, is not undefined for any x in the domain. Okay, so there's not really a lot to put on our number line. We don't have any like second derivative analog of a critical point here. We don't have any points where g double prime is 0 or where g double prime is undefined. So when we draw our number line, the only numbers that we'll put on that number line are the x values that give us those vertical asymptotes. So we still have a little bit of work to do, but not much. We don't get any points of inflection because we're not going to have any points on the graph where the function is changing from concave up to concave down. So we keep going. So we make our sign chart now for g double prime. List your two vertical asymptotes. Since g double prime was never 0 and g double prime was not undefined for any x in the domain, that's okay. And this is after I've simplified that numerator. We still can examine concavity on these three intervals, the intervals defined by those two vertical asymptotes. Our graph is a rational function, so it's going to have branches. It'll have a branch over here and a branch in the middle, and it'll have a branch on the right. We just want to know on those branches, is the graph concave upward or concave downward for each branch. Now this is all a little bit simpler if we factor that denominator further. X squared minus 4 is a difference of squares. So we could call that x plus 2 and x minus 2. And since we're cubing the product of those two, you don't have to show that step if you don't want to, but I wanted to show you just so you know where this is coming from. That means you cube the factors separately. So we'll have x plus 2 cubed and x minus 2 cubed. It'll be easier to substitute into those factors than into that one when I make my sign chart over here. So let's substitute the factors. Got a 16 times 3x squared plus 4. Does not matter what x is. That's going to be a positive number plus 4 times 16. It's going to be positive. So that's our numerator. Now in the denominator, I've got this factor and this factor. X plus 2 cubed and x minus 2 cubed. So I'll substitute in negative 3 over here. Negative 3 plus 2 is negative 1. Negative 1 cubed is negative. On this interval, negative 2 to 2, plug in x equals 0. 2 cubed, it's 8, it's positive. On this interval from 2 to infinity, substitute any x value you want from 2 to infinity, maybe 3. 5 cubed is positive. Do the same thing with this one. Substitute in negative 3. Negative 3 minus 2 is negative 5. Negative 5 cubed is negative. Substitute in 0. Negative 0 minus 2 is negative 2. Negative 2 cubed is negative. Substitute in 3. 3 minus 2 is 1. 1 cubed is positive. So I've got a positive divided by a negative times a negative. So that's going to be positive. And then I've got a positive divided by a positive times a negative. So that's negative. And then we've got a positive divided by a positive times a positive. That's positive. So the graph is, remember, this is the second derivative now. It's not increasing and decreasing. The graph is concave up over here, concave down over here, and concave up over there. The graph is concave upward, concave downward is actually the right way to say it. Graph is concave upward on negative infinity to negative 2 and 2 to infinity, and concave downward at or on the interval from negative 2 to 2. It's very tempting to say that you've got points of inflection at negative 2 and 2, but you don't. X equals negative 2 and x equals positive 2 are not in the domains, or the domain of this function. So G does not have any points of inflection. Okay, so we did increasing and decreasing. We looked for intervals where the graph is concave upward and downward. We found relative extrema using the first derivative test. Now let's use the second derivative test to confirm. We decided there are no points of inflection, and now we'll sketch. So according to the first derivative test, we've got a relative max at x equals 0. Let's prove it using the second derivative test. First, you find your critical points. And we already we got a single critical point. It was x equals 0. Then you compute the second derivative. And we already have done that as well. We got 16 times 3x squared plus 4 over x squared minus 4, quantity cubed. Then you evaluate this at the critical point. So critical points where the slope is 0, or potentially where the slope is undefined, but for the second derivative test, the slope is always 0 because you're able to take the second derivative. You replace x with 0 and you get 16 times 4 in the numerator over negative 4 cubed in the denominator. So that's negative 1. So that's a second derivative and it's negative. What does that tell you? It tells you that the graph is concave downward, and since the first derivative is positive, we're at the top here. So if the first derivative is 0. The first derivative is 0 because we're at a critical point, we're at the top. So the graph is concave downward, we're at the top of the graph, so that has to be a relative max. So g of 0, which we calculated earlier, was negative 1. That's a coincidence that it happens to be the same as the second derivative. It's not always the case. This is a relative max by the second derivative test. Okay, now the last thing we want to do is put all of this information together to graph our function. And I'm so sorry, I'm just going to step away for a minute. My doorbell rang. Okay, sorry about that. Okay, so we want to graph the function using all of the information that we just found. So we know, what do we know so far? We know the graph is increasing on negative infinity to negative 2 and negative 2 to 0. We know the graph is decreasing on 0 to 2 and 2 to infinity. We know the graph is concave upward on negative infinity to negative 2 and 2 to infinity, and it's concave downward on negative 2 to 2. We've got a relative max of negative 1, and that occurs at x equals 0. And we've got vertical asymptotes, x equals plus or minus 2. And we don't have any points of inflection. Okay, so let's do this. First, I'll draw the vertical asymptotes. X is -2 is over here, x is +2 is over here. When x is 0, y is -1. That's supposed to be a relative max. And I think I want to make a little chart like we did on the last problem, using a number line again. With all of these intervals that we were given, we mentioned 0, we mentioned 2, we mentioned -2. So I want to draw all of those on this number line. And then remember that I've got a vertical asymptote right here and a vertical asymptote right here. Well, what do we know? On this first interval, the function's increasing. And then -2 to 0, it's still increasing. 0 to 2, it's decreasing. 2 to infinity, it's decreasing. It's concave up on this interval. And it's concave up on 2 to infinity as well. And on -2 to 2, the graph is concave downward. Okay. Now, on this part, we're told that it's increasing and concave up. Now, concave up generally looks like this. But if it's increasing and concave up, that means you're only talking about one side of this little graph. If the graph is increasing and concave up, it's going to have that behavior. And I think that makes sense when we look at our function g of x equals x squared plus 4 over x squared minus 4. I would expect that to happen over here, even though we haven't discussed it in a little while. Since the degree of the numerator and denominator are the same, this one also has a horizontal asymptote at y equals 1. Okay, so we're going to have a graph that's increasing and concave up, concave upward, and I think it's always going to be above that line, so we'll get that. So it's increasing concave upward there, that's taken care of. Now on this one, it's increasing and concave downward on one side and decreasing and concave downward on the other. That's going to look exactly like this little parabola facing down, increasing and concave down, decreasing and concave downward. So you're going to see that. And over here it's decreasing and concave up, so when I draw my little concave up parabola, it's the decreasing side only, so it's going to have that behavior. It's going to look like that. So that's our function, g of x. Now again, the way we do this, always find the domain first. Then you find the critical points of the function. So you take the derivative, set it equal to 0, and think about any x values in the domain for which the derivative is undefined. All of those plus the asymptotes have to go on this number line. Then you conduct a sign analysis of the first derivative to get this. If the first derivative is positive, the function's increasing. If the first derivative is negative, the function's decreasing. If the function changes from increasing to decreasing at a point where either the derivative is 0 or the derivative is undefined, but it's in the domain, then you've got a max. Or the other way around, you'd have a min. But remember, if you have an asymptote there, any changes in sign mean nothing. There are no relative extrema at points that are not in the domain. So we've realized that we have an extrema relative max at x equals 0. You got to find the y value that goes with it. That's actually the relative maximum value of the function. It's the y equals -1. Then for the next part, you're basically doing the same thing with the second derivative that you did with the first derivative. We don't call them critical points. I wish we had a name for them, but unfortunately we don't. But we're doing something similar to what we do when we find critical points. We take the derivative again, we set the derivative equal to 0 and solve, and then you also think about x values in the domain for which the second derivative is undefined. You have to consider them both. This time our second derivative was never 0 and our second derivative was never undefined for any x in the domain. Once you do that, you do for the second derivative what you did for the first derivative, creating another sign chart, but this time you interpret those signs differently. Second derivative being positive means the graph is concave up. If the second derivative is negative, that means the graph is concave down. And if there are no x values where it switches in concavity, the graph does not have any points of inflection. Now this looks like it switches in concavity at -2 and 2, but those aren't in the domain, those are asymptotes. So we can't have a point of inflection there. Now the second derivative test is not necessary, but it can confirm what we calculated using the first derivative test. You can find your critical points where the derivative is 0, take the second derivative and plug in those critical points, and if you get a negative number for the second derivative, that means the graph is concave down. If the second derivative is negative but the first derivative is 0, the graph is concave down and you're at a point where the slope is 0. So you have to be at the top, so that's a relative max. If the second derivative happened to be positive, then the first derivative would be 0. Second derivative positive means it's concave up, and we'd have to be at the bottom, so that would be a relative min. Okay, then we put all of those pieces together to sketch a graph. Now this is probably not a perfect graph. I mean, there are not even any y values except for that one y value. But this tells me a lot about the graph. I know it's increasing here, it's increasing here, it's decreasing here, and decreasing here. It's concave up on this interval and this interval. It's concave down on this one. We've got a relative max right there, even though it looks like it's not the maximum it should be. And then we've got 2 vertical asymptotes and no points of inflection. So that's it for this video.